Hello everyone, I'm Erdem Bıyık. I'm an assistant professor from the University of Southern California. Today I'm going to present our work, GABRIL. This is a collaboration with the students from our university, Amin, Fatemeh, and Yutai. We were hoping to give this presentation in person, but some of us cannot leave the US and some of us cannot enter China. So it will have to be an online presentation. Robot learning community has been pushing for training generalist robots by using large robot datasets, similar to large language models. However, as this image visualizes, the amount of data that we have in robotics is nowhere close to large language models. As a result, the community has adopted this pipeline of pre-training a model and then introducing a second stage where we fine-tune this large model with some extra human demonstrations that are in distribution. And there are many papers that try to do this. And if you look at these papers, you will see this common problem that they usually require more than 100 demonstrations for fine-tuning. This is not feasible in real world because everyday users will have difficulty teleoperating or using these other interfaces that we have for demonstrating an expert behavior. And it also 100 demonstrations is going to be too many for practical applications. So the first question we ask is, can we extract more information from each expert demonstration? Before I introduce our method, I also want to talk about a second problem, which is causal confusion. Now, to illustrate this with an example, think of a case where we are trying to use imitation learning to train an autonomous driving policy. Now, in the dataset, there will be many time steps where the car is stopping in front of a red light. So the driver is pushing the brakes. Now, what is in the observation of the policy? Well, there's the red light in the image, and there is also the information that the car's speed is 0. Now, it is possible and very likely that the learned policy with imitation learning can incorrectly associate pushing the brakes action with the speed of the car rather than the true causal factor, which is the red light. This brings us to the second question, which is, can we train the policy to focus on causal factors and not spurious correlations? Our insight in GABRIL is that the demonstrator's eye gaze carries information about causal factors. Like, think of the autonomous driving case. If this is the scene in front of you while you are driving, what are you going to be looking at? Well, you are going to be looking at the pedestrians and probably the stop sign because those are what is important for your next action. To make sure this is the case in different environments, we also conducted some studies where we asked people to play these Atari games, and in these videos, the red dot shows their eye gaze. As you can see, often their eye gaze correlates with what is important in the task or saliency in the task. So we created this interface, and we asked people to drive this driving this autonomous driving simulator CARLA or play some Atari games. We created this huge data set of expert demonstrations augmented with their eye gaze, and we are publicly releasing this data set. Now, let's talk about our method. In regular behavioral cloning, usually the data is just observation and action. And what we do is we train a policy that learns to map the observation to the actions. In our method, in addition to observation and action, we also collect the eye gaze of the user as an additional data modality. And then we use this gaze information to create a gaze mask, which we later use to regularize the attention of the policy. So in this case, it's a CNN policy, so we take the activations of the convolutional layers and we use the eye gaze to regularize them. When we do this, we see that the policies that are trained with GABRIL, they indeed pay attention to the causal factors, whereas standard behavioral cloning may often fail to do so. And in turn, this gives us better data efficiency and it mitigates causal confusion. Here we are seeing some results from the CARLA simulator where we are using the learned policy to drive in seen or unseen routes. And as you can see, GABRIL improves performance against the different baselines. And results are similar in Atari. In both normal environments and causally confounded environments, we get much better results when we do this eye gaze regularization. We have many more results that I don't have time to go over due to time limits, but I encourage you to check our paper as well as our website to get the code and the dataset that we have for the experiments. We are now excited to extend this regularization idea to temporal causal confusion cases, as well as trying to use vision language models to annotate the saliency instead of using human eye gaze.